Hi, my name is Fernando Daniel Martinez Cortez, and I am a digital art student at the University of Guanajuato. This work was developed together with Dr. Uriel Aile Hernandez Belmonte, PhD professor of art at the University of Guanajuato. And today I will present the topic of resource-efficient shader implementation for immersive narratives on legacy mobile virtual reality platforms. This presentation focuses on the rendering pipeline of Sentinel, an immersive narrative project designed for older mobile virtual reality hardware, specifically with the Oculus Go. The main objective is to explain how custom shaders, simplified lighting, and outline rendering, GPU instancing, and controlled post-processing can help preserve a stylized visual identity while respecting the technical limitations of legacy VR devices. The central problem of the research is that in mobile virtual reality, the image cannot be understood only as a visual or artistic result. In traditional media, we might think of visual style mainly as an aesthetic decision. However, in VR, especially on older standalone mobile devices, every visual decision also becomes a technical decision. Each shader, texture, material, light calculation, outline, or post-processing effect affects performance. These elements consume CPU time, GPU resources, memory bandwidth, and energy. For this reason, visual style cannot be simply be added at the end of the project as a decoration. It must be designed from the beginning, as a part of the rendering pipeline. In the case of Sentinella, the visual style is directly connected to optimization. The project uses stylization not only for artistic expression, but also as a strategy to make the experience technically possible on the Oculus Go. The rendering pipeline of Sentinella is structured around four main technical decisions. First, the project uses a custom toon shader instead of standard physically based rendering materials. Second, it uses an inverted hole pass to generate outlines, instead of applying a subtle edge detection filter over the entire screen. Third, it uses GPU instancing for compatible groups of meshes and materials, reducing the number of draw calls. Fourth, the project limits the Sentinella mode post-processing effect to a single full-screen bleed, while using layer mask to isolate special objects without requiring additional full-frame passes. Together, these decisions form a rendering strategy where the visual style is shaped by the technical limitation of the hardware. The project does not simply reduce quality. Instead, it chooses a stylized direction that works efficiently within the available resources. The toon shader follows a simple and controlled lighting process. First, the shader samples the albedo, which is the base texture multiplied by the material color. This defines the basic color of the object. Second, it compares the surface normal with the direction of the main light. This is usually done through a dot product, which estimates how much the surface is facing the light. Third, the result of this dot product is remapped into a usable range between 0 and 1. Fourth, a cell threshold is applied using a smooth step function around the shadow threshold. This creates a stylized transition between illuminated and shadowed areas. Finally, the shader combines the albedo, light color, cell factor, and an attenuation to produce the final toon lit color. The important point is that the shader avoids unnecessary physical complexity while still creating a readable and expressive visual result. The second major decision is the use of an inverted hole pass for outlines. Outlines are important for the visual identity of Sentinella because they help create a stylized, illustrative look. However, there are several ways to create outlines, and not all of them are equally efficient for mobile VR. Instead of using a full-screen post-processing outline, Sentinella uses a geometry-based method. In the inverted hull technique, the shader discards front-facing polygons and renders the back-facing geometry of the object. Then, the vertices are offset along their normals in world space. This creates an expanded version of the mesh, which appears as a silhouette around the original object. The shader writes to the depth buffer and returns a flat outline color. This means that the outline is generated from the object's geometry, rather than from a screen-wide image filter. The inverted hull technique does not remove cost completely. Instead, it changes where the cost happens. For example, a Sobel-based outline increases full-screen fragment processing. Its cost is applied to the entire screen, regardless of how many objects actually need outlines. This creates a high fill rate pressure, high memory bandwidth usage, and many texture rates. The inverted hull approach works differently. It adds an extra rendering pass to the objects that need outlines. This increases vertex processing and draw calls for those objects. The main disadvantage of the inverted hull method is that it adds an extra pass. If an object uses a tone shader and also needs an outline, it must be rendered once for the baselining pass and once for the outline pass. This results in 2 draw calls for each object in the scene. This means that if the number of outline objects grows, the number of draw calls also grows. For this reason, the pipeline needs a strategy to reduce the CPU overhead caused by repeated draw calls. That strategy is GPU instancing. GPU instancing is a technique that allows multiple compatible objects to be rendered together using fewer draw calls. Instead of sending each object separately from the CPU to the GPU, the engine groups compatible objects into the instanced batches. For this to work efficiently, the objects must share compatible meshes and materials. In Sentinella, this strategy is especially important for repeated groups of objects that can share the same texture. The fourth important system is Sentinella mode, a post-processing effect used in the project. This effect operates on a source rendered texture and writes the result to a destination rendered texture. The shader calculates a radial mask from the UV coordinates. This mask defines how far each pixel is from the effect center. Then, the shader converts the original color into a grayscale using luminance waves. Finally, it interpolates between the original color and the grayscale result, using the radial mask to control the affected area. The key optimization is that the effect is resolved through a single full-screen bleed. This is important because in mobile VR, each additional full-screen pass increases the amount of pixel processing and memory bandwidth usage. Sentinella also includes special objects that must remain visually distinct during Sentinella mode. A less efficient approach would be to apply additional full-screen bleed or create more intermediate rendered textures. Instead, the pipeline uses a layer mask and a temporary secondary camera. The main camera excludes the special layer mask and renders the post-processed result. Then, a secondary camera renders only the objects assigned to the special layer over the processed image. This approach avoids applying another full frame effect. It also prevents unnecessary objects from being rendered again and avoids creating additional intermediate textures. In this way, the pipeline isolates special objects while keeping the post-processing structure efficient. To conclude, Sentinella demonstrates how an immersive narrative can adapt to technical restrictions of legacy mobile VR hardware. On a device such as the Oculus Go, every visual decision must be technically justified. The result is a rendering pipeline that treats visual style not as an ornament, but as a technical structure. In Sentinella, resources efficiency does not reduce aesthetics. Instead, resources efficiency makes the aesthetic possible.